Okay, so we know that f prime of infinity is equal to 1 or goes to 1. There's more information about this that we can get. Okay, so if we were to, we know, okay, so if it goes to 1, we know then that thus f at infinity goes like eta. And it was actually found that this is plus a constant. We can come back to that later, plus higher order terms that decay. Okay. So we're going to use this to our advantage. And so the third step here is to form an approximant. This is all wrong. I actually had to go back and stop the recording. The third step of this whole process is to make up an approximant. Okay. And you can make up whatever approximate you want as long as it matches the large behavior. And then you might find something wrong with it later and you'll go back and tweak it. And that's what often happens. So, okay, make up an approximate. Okay, so we're going to make up one, call it f sub a for f approximate equals eta. And I'm going to do something wrong first, and then we'll see what happens. So eta, how about eta plus b plus something that goes away, okay, as eta goes to infinity. So one thing could be like 1 over a quadratic in eta, or 1 over a cubic in eta, or more generally, you could just say 1 over some series in eta. And I'm choosing capital A sub n, and I'll talk about that in a second. I'm introducing that here. Now, this certainly satisfies that f prime of infinity goes to 1, right? As eta goes to infinity, this fraction goes to 0, the b goes away, and the eta turns into a 1, right? And certainly, it also matches the eta plus b, right? For f as eta goes to infinity. Okay, so the fourth step here, and we might come back and erase this. The fourth step would be to say, you want to choose these unknown coefficients here, capital N. Choose the a sub n's such that the expansion of f sub a about eta equaling 0 equals your solution up to capital N, your power series solution, your exact solution. Okay, so let's just start working this out. Okay, so this means that f sub a is 0, we want to equal f of 0, which we know exactly to be 0. Okay, so let's work this out. So capital F of 0, this is going to be 0 plus b plus 1 over a sub 0, according to the formula up here above. And we know that lowercase f of 0, just a regular f of 0, is supposed to equal 0. Okay, I guess never mind. I guess this works out. This is fine. So this does work. Okay. So so we'll use this. This is not exactly what I have in the paper that we use, but I think it reduces to that. Okay, so this matches. This tells us that this gives us one of our capital A's. It tells us that a sub 0 equals negative 1 over b. If you choose your capital A sub 0 to be negative 1 over b, it will match the first initial condition or the first term in your power series solution. So we keep doing this. Let's just keep doing this. Okay, so how about f prime of 0? We want that to also equal f of 0. Oh no, here now we're getting into a quotient rule thing here, right? So we'll just do this and then we'll streamline this a bit. Okay, so from here, right, let's see, we're gonna get a 1. And then let's see, I'm just gonna do the chain rule. So it's gonna be negative. Geez, I don't know. It's going to be some function of the a's, right? So in fact, I think it's going to be a function of a0 and a sub 1, right? So do some quotient rule stuff. And it's going to be some function, bad choice of variables there. You're going to have an a sub 0 and a1 appear. Right, set that equal to 0, solve for a1. See where we're going with this? So then basically you end up with a system of equations. So to find the capital A's, you're doing just exactly this. You're saying f of a0 equals f of 0. See what happens, right? That equals a sub 0, right? F prime of a0, you want to equal f prime of 0, right? That's a sub 1. F double prime 0 equals f double prime of 0. That's 2a sub 2, right? Etc. Right? F a to the nth derivative of 0, capital Nth derivative. F capital Nth derivative of 0. That'd be capital N factorial a sub capital N. Right? So it's a system of linear equations. Oops. And you could write that system out and do a matrix inversion if you want. There's an easier way. Solve for capital A's. Okay, so that's what you do to generate, to brute force to find the capital A's. Once you have the capital A's, you put them back into your approximant here. And now you're done. So the next thing I want to talk about, so I didn't give you an easy way to find the capital A's, right? Like right here, you have to do a quotient rule. That doesn't sound fun, right? So, and then just imagine the nastier quotient rules you'd have to do as you move on here. So right now, I'm probably not selling the method, but I'm running out of time today. I'll pick this up and make another video tomorrow where I'll show you a very nice way to get the capital A's without having to form this system and without having to do any sort of quotient rules or matrix inversion or anything. Okay. So I know I didn't get to the real useful stuff yet in forming an approximant, but I hope that this provides a background that leads to that. Okay, and I'll probably re-record these and make this a lot smoother in the future. This is my practice run. Okay, have a good day, evening, afternoon, whatever time it is when you're watching this.